Yes, I wanted to talk to you about water, which is maybe not so surprising on that conference. But then again, like, if you're underwater roboticist, you're mostly interested in keeping water out of your vehicle, and this is where the interest ends often. But I want to talk about how to measure water, how to measure flowing water, what kind of information can you extract from the flowing water, and what you could do with that. So some of my talk will be devoted to how does it relate to robotics, how to use this information to better guide and control robots. But some of this talk will be devoted about just the environment, water environment, what kind of information is there in the environment, how to understand it better, and what can we do with the information in general. So when it comes to measuring water, it's actually fairly simple because you have, yeah, no, it works. You have just 3 parameters that you can measure. This is velocity, pressure, and then vorticity. And actually, things are even simpler in a way that there are only 2 equations in the world. Bernoulli equation and the Navier-Stokes equations that connect those 3 parameters together. So if you manage to solve those equations, you know everything about flowing water, which is not that simple, but anyway. Yeah, fluid dynamics made easy. But when it comes to the measuring part now, then these are normally the devices that we go in a field and we measure. We have fancy device in a laboratory, which I haven't shown them, for example, particle image velocimetry that gives you a very nice picture of the flow field. But those are impractical or very, very expensive to use in the field. When you go out and what you measure in natural environments, then you're more or less restricted to devices that measure the quantities only in one single point. You could put a lot of them next to each other or in an array, but that is gonna be like hugely, hugely expensive in the way. And you're also restricted to quite small sampling frequencies. Maybe 10 hertz, 5 hertz, 20 hertz, but turbulence is much, much more complicated things like that. So it means that if you're cut off the high frequency fluctuations of those quantities, velocity, pressure, turbidity, then you're also losing a lot of information. And my work has been, to a great extent, focusing on how to get the information from water from very many points and with much higher frequency. So I want to have a better distribution both in space and time, higher distribution both in space and time. And since a little funny gadgets that we have built in my lab, and I'm going to walk you more or less through them during my talk, and some of them are related directly to robotics and some are not directly related to robotics. And I also show you that if you have those tools for measuring now, then you also immediately have much more interesting applications that you used to have before. You can actually ask much more interesting questions and solve much more interesting problems. But these devices are still very, very rudimentary compared to this one here. I think the best device for distributed sensing, both in space and time, is a fish. And it has done it very successfully for over 300 million years, so there must be something that is, first of all, a very practical thing to do. And second, in the long term, it also gives its a survival in the water. So the organs that fish uses for sensing flow, a lateral line organ is a very big, very complicated organ. Nobody ever, no animal will develop an organ like this just because it's a fancy thing to do. It must be energetically optimal for the animal, and given that all the animals that live in water more or less have some sort of a capability of sensing flow at high frequency and distributed manner, it means that it's a reasonable thing to do. Some years ago, we tried to model the same kind of organ on a robot and see what kind of information we get out of water in this case, and how would we build better robots by using that information. And we came up with a prototype, which is now already several years old, equipped with, so to speak, artificial lateral line sensor, or capability of getting information from a flow at high frequency and distributed manner. And it works only in the lab. You could see that it's actually attached to a stick, so it doesn't do 3D, but still we could, in a laboratory flume tank, demonstrate that we could swim against the water, we could compensate for the drift, we could understand where are the flow patterns in the water, and how to save energy by swimming in an optimal way of controlling the robot with respect to the flow. And after doing that, we wanted very much to go outside of the laboratory. Even it's really difficult, everybody here knows it's difficult, but fluid dynamics in controlled environments is difficult already, but the patterns that you have in a natural environment, uncontrolled patterns, are much more difficult. But we really wanted to understand, if we take this little gadget out to the field, what do we actually could possibly perceive and sense with a sensor like that. So when the years went by, then we came up with a large range of different gadgets to take out to the field and try different things. And at the moment we're somewhere here where we have taken the rudimentary lateral line and put it on a commercial robot to sense the speed of the robot. And in the end, it turned out to be, you would say, kind of a trivial thing. So you would perhaps wonder that why did we take such a detour through bryology and eventually ended up with something which in aerodynamics is known for a long time already, a pitot tube. But it works very nicely for estimating the speed of the robot. The working principle of it is that you have 3 holes, as you said, these are the pitot tubes, and you're measuring differential pressure between those 2 holes here and those 2 holes here. And from the differential pressure, you can then estimate the speed. If you have a spherical thing like that, it's quite a simple equation called the Pitot equations that helps you to derive the free stream velocity from the pressure differences from here. And if you're not just facing directly to the flow where you go, which is quite reasonable that you don't if you have a robot, then if we put a little bit more effort in derivations and there's a geometry, we could actually also compensate for the sway and still understand where what is the free stream velocity. Christian is actually sitting here, and he's been doing most of the work in figuring out the equations and also doing the testing. And also, since we wanted to know the speed with respect to the flow, speed with respect to the water of the vehicles, and we were interested in filtering out all the self-motion of the vehicle. So we have a Kalman filter that takes an IMU data, takes the pressure data, and then throws you out the speed of your vehicle with respect to water in 2D. Some of the experiments have first done with a robot in Girona. Some of you maybe would recognize it. It's called a Spotless Robot. And then we specifically developed a casing for the robots that accommodates the differential pressure speed sensor. And here you could see what is the experimental results out in the field. So one is done by TVL and the Kalmar filter, and the other is done with a differential pressure-based speedometry and the Kalman filter, and they are pretty comparable results altogether. So you might wonder, why do you build a device which is not any better than TVL is, but it has several advantages. One of the advantages is it's a completely passive device, so it doesn't emit anything, and it doesn't take energy for emitting something, so its energy consumption is basically almost nothing. It's very small, so you can put the holes really very close to each other, whereas TVL is, as you know, a pretty bulky thing and you need a big robot. So TVL probably is not a good choice when you have a small robot because it takes all your space. And finally, it's much, much less expensive. So 3 advantages at least. But there's also a 4th advantage that we figured out quite soon during the experiments. Here is an example where we are in a harbor in Girona and go next to the wall. And you can see that the DVL gives you reflections for the harbor constructions, whether the passive TPSS works still very well. So there are environments where acoustics simply don't work or work very badly. So that is exactly when you are close to underwater infrastructure somewhere, or vegetation, or there's also some cases where you simply don't have enough particles in a flow to reflect back from, say reflect back the acoustic signal. So in this case, probably this device would be superior. Here's a next example where we made it even more optimal, so you could play and plug it on any robot there is, and this is now with an LAUV in Trondheim. So the device here is this little gadget here, just duct tape to the robot, and we go in the Trondheim fjord with currents and against the tidal currents. So from here you can see a difference between water-locked TVL and a bottom-locked TVL. So bottom-locked TVL measures your ground speed, and the water-locked TVL measures your water speed. Sometimes you can't use bottom lock because you just don't have a bottom. The bottom is so deep that you can't see it, and you have to just rely on a water lock. So TPSS is equivalent, a mechanical equivalent to the water lock sensor, TVL. Here, there's a big difference between the ground speed and the water speed because the vehicle is going with the currents. Which way does it go? With the currents? Oh. Against the currents, okay. Because it's going against the currents, but there is much less difference because I think there we're going next to the slack water, which means that the ground speed and the current speed are more or less equal to each other, and you can also see that all the 3 measurements are converging here. So it kind of works as it's supposed to work, as you would expect this device to work. But that's now for measuring a velocity. Velocity is like a DC signal, right? We want still to average the velocity readings in a way, but just taking advantage of that, this pressure sensors are actually capable of sampling very, very fast. I think we could go like up to 500 hertz or something. We could actually also measure very well pressure fluctuations in the water. And that's, some years ago we made experiments in the river going around with a artificial lateral line sensor, putting it in different places in the water, just to see what would we get, or what does a device measure. And the interesting thing is that although there was a famous Greek philosopher who said that you cannot step in the same river twice. So it's actually busted, you can. Because we could understand in a flow there are definitely salient flow features, things that don't change for a very long time. You go back, for example, 2 months later and you put your sensor in there and you look at the signals and say, I've been here. And you put in a different place and say, that's a different place. And in that way, we came up with an idea that we could use it for navigation, for example, as features, but also to understand the natural environments, to categorize natural environments. Whereas, for example, in river science, there are a lot of applications where people do it subjectively. They just go along the river banks and they work down, this looks like category 1, this looks like category 2, but you don't have like an objective measurement, what does it mean? And we thought we could provide something like that. Here is also an example, a pretty recent one, when we went out in a Trondheim fjord, and I don't know whether you recognize or see, this is a blue eye robot for which you have a demonstration now. And on the top of this blue eye robot, it's our little gadget here. So we're driving through different places and see whether if we put the robot in the water, we see something. Here is, I don't know whether you can see, there is a line which probably is like a front where a river bloom comes out and then mixes with the ocean water, and you could see the line here. And if you drive back and forth through these lines, then you get these interesting fluctuations every now and then. I'm not really sure what they mean, because it's a very preliminary, just an example, what could it be? But definitely there is something in the water that could be like a salient feature in this case. We did much more work on that in rivers. It's actually what we did for several years now, just going around in the rivers in the whole world. This one is taken in Japan, and putting our fish sensor in the water to see what if you were fish, what would you perceive? And then we visualize those. For example, this is now the distributed pressure sensor array, and this is how we perceive the pressure fluctuations in this case. And you could again see that this spot is different from this spot here, obviously. Why would anybody want to know that? For example, if we now make a preference studies of the fish to correlate their behavior to the flow characteristics. This is now a tank study where we track a fish in a in-house river, so to speak, and measure the characteristics. And we can see that fish prefer certain places that they don't like to be in others. And why is it important from a preservation point of view to perceive the fish habitats, understand their behavior, but also understand, for example, the behavior of migrating fish, how they go upstream, how they detect what is called a attraction flow, sort of salient features in flows that makes them to go upstream. And we got a lot of interesting new knowledge on that. So if you look at this one, it's actually now also sensors are Eulerian sensors in a way, so they are point measurements. We put it in a certain place on the ground, and then we stay there and we measure. So water is moving, but we're staying at the same point, like, as opposed to in fluid dynamic when you go to Lagrangian measurements. Lagrangian measurements is as if you were a particle and you were going together with the fluid. So you get a different view of the fluid in this case. For that we have another gadget, I'll show you. So it's again the pressure sensors here you might recognize, and this is an IMU. And then we just throw them in the water, and then we measure the signals. Here is an example here, for example, going down a waterfall, and these are pressure signals, these are acceleration signals. And and it's quite easy to say that you have one waterfall here, and you have another waterfall here, and you have quite a smooth flow in between. Or if you want to do in technical terms, then you have subcritical flow here, you have supracritical flow here, and subcritical flow here again. And looking at those things, you could say, okay, this is what river hydrodynamics is called a step riser, and there is another step riser, and between you have a chute. So this is how hydrology people characterize flows. And you know that this is true because you can see the flow here, and you have a ground truth. So what happens now in a case when you don't have a ground truth? You're just looking at the pictures and you want to solve the reverse problem. You just have those plots and you want to understand how is the morphology of the river looking like. Why would you need that? Here's one example why would you do that. It's a glacier. And when the glaciers are melting, then you have canals in the glacier. So the melting water is making canals going through the glacier, and then nobody knows what it's doing. Nobody knows what happens, but eventually it comes out somewhere in a glacier outlet. And we wanted to know what happens in between. So we went up to the glacier. First we tried again the ground truthing thing. So you can see our little gadget floating down it, and you can see the plot here. And after a while, maybe you know, if you keep watching it, I've watched it so long, then you understand that the behavior of the little drifter is actually correlated to the morphological features. For example, this is a circulation zone. If you're going down the step riser and you keep circulating there, you can't get out until you finally can. And this is something which is called a chute because it's like a long slide going down, and there's not much happening at the same time. And then you go again to a step riser, you get like little bumps here and there once in a while. And after a while, you start understanding how the features are correlated to the morphology of the channel. Of course, we need to do a little bit more signal processing here, but we haven't managed to do that yet. But actually, we got a confirmation here that we have repeatable measurements, which is not so obvious to do because it's a very high Reynolds number flow. You would expect it to be pretty chaotic measurements, but after you throw the things in like 30 times, you could see that all those things are converging and you get more or less the same patterns after like 30 runs and 50 runs or something like that. And now you could go out to a more bigger scale experiment where here is the entrance, which is called a moline, so the water goes into the entrance and there is the outlet. So in the middle there is a channel which nobody knows how the channel looks like, and this is where we have thrown in drifters into the channel. It's a channel input here up on the top, and between input and outlets there is about 1 kilometer. So it keeps traveling, and eventually it comes out from here. And it's exactly the same thing as with underwater robotics, like everything, the most difficult parts of every operation is retrieval and deployment. Yeah. But we managed to recover almost all of the drifters, so we were very proud of ourselves. And after a while, again, if you look at the signals, then what you see is that that's probably a place where we just throw them in, and then you have, obviously here, one step riser waterfall, then you have another waterfall, and then you have a third waterfall, then you have more or less smooth right, and finally this is probably where I'm taking the sensor and throwing to the shore. So here is a cascade of 3 step rises in the beginning, and then is a pretty long, smooth chute up to the end in this case. But this is very preliminary data, just, you know, a qualitative or illustrative data, so we still have to go through all the number crunching. So, yeah, Finally, I wanted to talk about yet another gadget that we have. It's very hard to see how could this thing be related to fish anyhow. And it was actually a problem for us because now we're coming to a large-scale flows, and it's not so obvious that if you have sensors that work on a small-scale fluid, that all the technologies that you develop, that they scale up to high Reynolds numbers. In this case, we have now a stem here, a vibrating stem, and the other modality is pressure sensing. So we put those two things together, put the sensors again in a flow in a distributed way, and now we have modeled and figured out from the vibrations of the stem what is the water velocity. And the other modality, which is pressure, gives us some extra information, but also higher order fluctuations. So we can do some number crunching again. And again, this is a river morphology study. So again, we go around, we put our sensors in different places, we measure, and after a while we go back, we do some classification and say, okay, this place is different from this one, hydrodynamically different, but you know, the third place is pretty hydrodynamically similar to the second one, for example. So it's again some sort of an objective classification of the flow. If you want to go like more bolts, and then is a very recent study from this spring. It's conducted in Orkney, north of Scotland, which is allegedly the windiest place in the whole Europe. And between the islands, there's around narrow straits where tidal currents come in and out, very, very fast flows, and very much turbulence, very high energy flows, how they call it. So we wanted to understand how those high energy flows are looking like. We took working boats and we took a small frame. Eventually, you can see the size of the frame here, and we put sensors on the flame at different places. So we have like a square of a matrix of sensors. And then we turned off the engines of the boat and just drifted through the water to see whether we see different patterns of turbulence. And again, we haven't gone through the data very well yet, but you could see sometimes you have like higher order vibrations, and you have a smoother region, then you have again higher vibrations. And again, one of the advantages of mechanical devices is that you don't have to bother with reflections from surfaces or particles or acoustic noise anyhow. And this is now where the frame is on the bottom of near the island of Orkney, where big ocean waves are coming in from the Atlantic. And it's inside of a kelp forest. You could see the kelp forest is swinging back and forth, and this is the frequency of the ocean waves. And if you now resolve these sensor readings here in the frequency domain, you could actually figure out what is the frequency of the waves coming in, the largest waves. And you can also figure out that there is very little higher order harmonics. So the waves that makes an impact on the ocean floor is only the biggest one. And here is just a comparative example where the tidal low is very, very, very high. So you could see actually here is a little stem, and it's vibrating like hysterically already. So it's almost saturated, and this flow is there about 4 meters per second. But what's interesting here is that if you have a frame like that, and you have some sensors in the kelp forest and some above the kelp forest, and you can also figure out how much drag is removed by the vegetation in the flow. You couldn't anyhow do it with acoustics because you would just get noise back to you. So it's probably the only way of understanding the dynamics of vegetation. Finally, there's one more study with the same kind of sensors, now put it in a square on a seabed, and we wanted to understand the impact of the ship wakes to the coastal region. It's a problem in where I live in Tallinn, but it's actually a problem in almost every harbor in the world, so that you have very high energy waves from the ships that might possibly also destroy the coastal regions. And so we submerged the frame into the sea, and then it was staying there for like a couple of weeks or something, and just recording the signals. And here is an example when a ship goes by. It's now recorded from a bottom, and this is recorded from a surface. So you could see that only the 3 most energetic waves actually reach the bottom. Everything else here is just gibberish, wind-induced waves and something else, but those 3 waves actually have an impact to the sediments. And again, this is something you couldn't do with acoustics, because you basically are on the seabed, you're measuring at the seabed. If you put an ADCP or something that you're too much above the seabed to see impacts like that. So it works very well near the surfaces. So ship wake has a certain structure which doesn't change much. It's called a Kelvin wake if you're in a subcritical flow. And now when you're looking at the pressure signals of the same sensors, you can actually see how the wake is projected to the pressure reading. So you have here a transverse component that gives you here a horizontal line, and then you have a diverging component that gives you this line when the ship goes by. And now the angle of this diverging components would give you the speed of the vessel. And you could also find out the distance of the vessel from that. So for the detection, you could see how the ships are going by, and after a while, we haven't done it, but I'm quite sure that with some number crunching, we could also say which vessel was it this time, and then match it to the schedules of the Tallinn harbor. But speed is also quite reliable. So most of the speed of the ship now, compared to AIS coordinates or readings, are pretty close to the ones that we have estimated here. And we can also figure out the distance of the ship. So this is our array here. Here somewhere is a port of Tallinn, and these are the leading lights to the port of Tallinn. So ships are coming back and forth in here. And if you look at the distance estimates, the distance estimate puts most of the ship on the leading lights to the port of Tallinn, so it can be very wrong in this case. Finally, almost final slides are even a bigger scale and bolder experiment where we have the same kind of sensors put on a slope of a coastal slope of the Baltic Sea, because the oceanographers wanted to understand the thermocline dynamics and halocline dynamics at the coast and at the slope. So thermocline is something where you have layers of water with different temperatures, and they're not mixing very much with each other, but they're creating very interesting dynamics, which is not very well understood. And halocline is then when you have layers of different salinity close to each other, and they're not mixing very well. But when those haloclines and thermoclines are now interacting with the slopes, and you get also a 3-dimensional flow pattern or dynamics, which is not very well understood. What is the interaction of the continental slope and the rise and fall of the thermoclines? So this is what we try to measure with the devices like that. The first one is about 15 meters deep, and the last one is 74 meters deep, and they're coming next to each other. And again, something you cannot do acoustically, because you have to be very, very close to the slope to understand the rising and falling currents here. So this is just the measurements that I was taking before coming here a couple of days ago. The experiment is still going on, so we deployed the sensors in July, and we're taking them out in the end of October when they start fishing in this area. And you could see, for example, this unit, which is 60 meters deep now, the direction of the current descent is changing, and also the magnitudes of the currents are changing. And keep in mind that in the Baltic Sea there are no tidal currents, so it's not a dynamics of the tidal currents, but it's only the dynamics of the thermocline motion that comes from it. Again, this is just a preliminary qualitative data, just shows that we can get data, but you know, the analysis and modeling based on the data, it's still something that the oceanographers have to do. Right, so that was pretty much all my gadgets. And again, the conclusion would be that there's very much information in this water that we're not aware of because we have no devices for measuring. If you get those devices, then we get new applications and new knowledge.